All right, folks, let's take a look at a couple of more basic examples. This is the integral of 2 over x squared minus 4 dx. We could do a trig substitution here, but it's not necessary. First of all, this is proper, as the degree of the numerator is less than the degree of the denominator, so no long division required. That's nice. But we do have to do some decomposition here, so aside. 2 over x squared minus 4 is 2 over x plus 2 times x minus 2, which is some kind of a over x plus 2 plus some kind of b over x minus 2 when we decompose it properly. So let's figure out what a and b are. Now, technically, we don't have to figure out what a and b are until the end of the problem. If you wanted, you could say that this is equal to the integral of a over x plus 2 plus b over x minus 2 dx. And since those are constants, there's nothing stopping you from factoring them out of the problem. And so I think I'd like to state really quick that I watch a lot of people kind of give up early on these integrals because they can't figure out what a and b are. If there's a lot of different variables, a, b, c, d, they give up because it's a daunting task. But I don't need to find out what a and b are to show you that I can at least integrate this. This is a times the natural log of the absolute value of x plus 2 plus b times the natural log of the absolute value of x minus 2 plus an arbitrary constant c. So the question still remains, what are a and b? So using this equation here, the decomposition, I can figure out what a and b are by multiplying through by the common denominator. That is, 2 has to be equal to b times x minus 2, a times x minus 2, plus b times x plus 2. And if I lost you there, you can either think about this as getting a common denominator and then setting the numerators equal, or if you just take this entire equation and you multiply through by the LCD. Let me move this over a little bit. If you multiply through by the LCD, which happens to be x plus 2, x minus 2, you'll see that as you distribute this to the first term, the denominator cancels and you're left with 2. As you distribute this to the a term, the x plus 2's cancel and you're left with an a minus 2. And then as you distribute it to the b term, the x minus 2's cancel and you're left with b times x plus 2. In either case, we can use the cover-up method here. If x is 2, we get 2 is equal to a times 0 plus b times 4, in which case b is equal to a half. And if x equals negative 2, then 2 is equal to a times negative 4 plus b times 0, which says that a is negative 1/2. So our decomposition then becomes negative 1/2 times the natural log of the absolute value of x plus 2 plus 1/2 the natural log of the absolute value of x minus 2 plus c. And if you were all about log rules, you could consolidate this to the natural log of the square root of the absolute value of x minus 2 over x plus 2 plus an arbitrary constant. But that's not strictly necessary. Anyway, partial fraction decomposition made short work of that integral. Let's try another one. This will be our last example for today. This particular expression is improper. And so we have to use long division before we even begin to decompose it. Before partial fraction decomposition. So what are we going to do here? We're going to do x squared minus 0x minus 1 divided into x squared plus 0x plus 1. Please note my use of placeholders. This is your review for long division, placeholders. and then we need to multiply the leading term of our divisor by what is ever necessary to turn it into the leading term of our dividend there. And so x squared times what equals x squared? Well, that's 1. 1 times x squared is x squared minus 0x minus 1, parentheses, subtract. Students forget the parentheses and then jack the sign up. Be careful. That's 1 minus a negative 1, which is 2. This is our remainder. And what this tells us is the integral of x squared plus 1 divided by x squared minus 1 dx is equal to a quotient of 1 plus a remainder of 2 over the divisor. Now, if you're paying attention, I'll show you something clever. Pay attention. I'm probably not going to explain this as usually it falls on deaf ears, but check this out. Watch this. This is crazy. Watch this. Don't blink, okay? What did I do there? I pushed the 1 off to the side. Boom. And that's called being clever. Yoink! Nailed it. Anyway, back to the decomposition and the integral. This is equal to the integral of 1 dx plus the integral of 2 over x squared minus 1 dx. Now this is easy enough. That's just x. What we need to do here is some decomposition. That denominator, I guess I'll put this information in here since it's everybody's first time. 2 over x squared minus 1 is 2 over x plus 1 times x minus 1 when we factor the denominator. And that's going to be some a over x plus 1 plus some b over x minus 1. And we need to figure out what a and b are, so let's do that. If we multiply through by the common denominator, we'll get 2 is equal to a times x minus 1 plus b times x plus 1. Again, what I have done there is I have taken this expression and I have multiplied through by the common denominator to eliminate the fractions. X plus 1, x minus 1. And as I do so, I will eliminate both denominators of my first product, leaving me with 2. And then I will eliminate the x plus 1s, leaving me with a times x minus 1. And then when I distribute to the b term, the x minus 1s will cancel, and I'll be left with b times x plus 1. And if you do that enough, you'll get pretty good at it. And that's how I got this result here. So very quickly, if x equals 1, let's use the other method. If I multiply this out, this is 2 is equal to ax minus a plus bx plus b. And if I collect like terms, this is a plus b times x plus negative a plus b. And on the left side, I just have 2. Now, in order to use the strong sense of equality, I have to have a polynomial on both sides. This is 0x's plus 2, which tells me that whatever a plus b is, that has to equal 0. And whatever negative a plus b is, that has to equal 2. So that gives rise to the following equations. A plus b equals 0, and negative a plus b is equal to 2. That's our system of equations. And probably the easiest way to solve this one, you could use substitution. I'm going to use an old school technique called elimination, or the addition method. And if I add those two equations together, what I get is 0a plus 2b is equal to 2, in which case b is equal to 1. And if b is equal to 1, then a is equal to negative 1. And that tells me that what we have is the integral of 2 over x squared minus 1 is equal to negative 1 over x plus 1 plus 1 over x minus 1 dx using that decomposition. And what I'm going to end up with now is x minus the integral of 1 over x plus 1 dx plus the integral of 1 over x minus 1 dx, which is x minus the natural log of the absolute value of x plus 1 plus the natural log of the absolute value of x minus 1 plus c, which is x plus the natural log of the absolute value of x minus 1 over x plus 1 plus c. And that is our antiderivative. So what have we done so far in day one? We've only dealt with integrals that are decomposable and have denominators that have non-repeated linear factors. Although this one I had to do long division because it was improper, and this one was proper but still had non-repeated linear factors. So that's all we've done with. Tomorrow in day 2, we're going to deal with some more advanced situations.